Voilà.
En direct, et quand lui il décidera.
Et voilà, ça y est, c'est reparti.
Okay, we're back. This is
Hello.
time the real thing. Hey.
Hey. Bah, écoute, c'est nickel.
Great. So I think we have the good hangout now. Just waiting for everybody to be here. It seems the light is good for everybody, so it's good.
Nice.
Okay.
Écoute, là, ça m'a l'air.
Okay, so I think it's working on my side.
Et est-ce
Attends une
que
seconde, je vais chercher Thomas.
ouais, et est-ce qu'il voit le bouton après pour rouge pour
Tu vois le bouton rouge là, enregistrer et diffuser? Enfin,
qu'il faudra cliquer tout à l'heure?
Ouais, moi je l'ai là, diffuser la vidéo publiquement.
D'accord,
je
très
vais
bien.
chercher Thomas, j'arrive.
Ok, cool.
Pas les gars, ça.
Attends, là, je vais surtout, hop, je milite pour la Palestine, tac.
Voilà. Okay, can everybody hear me?
Yes.
Yes? Okay.
Yep.
Should we try to do a mic setup? Trying if the mic are really working? Okay. So we can start with Aaron Sean. Can
Yep.
you try? Yeah, okay. Your mic is working.
En mon avis, on peut raccrocher la Daisy, non?
Okay, great. Then do we have David Singleton? Can you say
Hi folks, this is
Right.
David.
Great. Awesome, it works. Pierre-Yves, can you hear
Yeah,
us?
good to be.
Okay.
Hello.
Alors Pierre-Yves, I don't see you, mais écoute, je sais pas.
You don't see me?
I see you on the big screen, but on the small vignette, I don't see
Ça marche, hein. I see you.
you. Oh, ça marche? Okay, so
Ouais.
it's fine. The moderator see you, so it's fine. Then we have Radu.
Hi there, good evening. Radu from Dublin.
Très bien. The mic works, so it's great. Then we have Rich.
Yes, I'm here.
Okay, the mic is working as well. Did I call everybody? Yeah, okay, so we're waiting for Frédéric Kaplan, who is not here yet. And that's it. Pardon, bah vas-y.
Il est là.
Et Pierre-Yves, il est là. En fait, il est en blanc, là. Mais tout le monde le voit à l'écran, mais sauf que nous, on le voit pas en vignette.
D'accord.
Ah oui, c'est vrai.
Voilà, il affiche en grand. Vas-y, dis-tu bonjour.
Ouais,
C'est,
je te laisse.
On n'a pas encore commencé, c'est juste...
Je vais faire, moi.
Okay.
Tous les deux.
Okay, so we are waiting for two more people. We are waiting for Mériard and Frédéric. C'est peut-être lui qui a appelé.
Hello.
Bonjour.
Salut Thomas.
Salut. Salut qui arrive. Hello everybody. Ah oui, c'est vrai.
David, là, je raccroche moi, hein. C'est bon à mon avis pour le
Ah,
téléphone.
j'ai oublié pour le téléphone.
Ok.
Et en fait,
Bon. Donc a priori, moi de mon côté, là, je peux quasiment déjà me déconnecter ou comment ça se passe?
quasiment si tu veux. Et dès que tu vois que c'est parti et qu'on te dit Fred, tu peux y aller, tu cliques.
Ah, il faut que je clique, ok. Non, vous commencez dans combien de temps là? Vous attendez encore les deux là, c'est ça?
Exactement.
Ok.
Voilà, Frédéric Kaplan.
Ok.
Hello Frédéric. Il va venir en vrai, je pense, juste après.
He sent an avatar this time.
He should be there soon. He should move soon. Salut Frédéric.
Bonjour, moi je vous vois. I see you.
Hello. You were just a photo, but now you.
Okay. Well, I'm going to put slightly more light.
Yeah, there's a bit of contre-jour.
Yeah.
Yeah.
Yes. This is Hollywood tricks. So we're waiting for Myriam, that will be the moderator of the. So here with me is Thomas Belama. Hello, everybody.
was the associate curator of the exhibition Mathematics, A Beautiful Elsewhere. So I worked with Pierre-Yves and Frédéric.
Your personal page? Yeah, on your personal page.
Ah, c'est bien là, Frédéric. Good lighting.
Oh, better.
And everybody can see Pierre-Yves in slide.
Yes.
Okay, just us.
Okay, because we cannot.
I think Claire is calling Meria right now.
It's okay. Yes, no?
Yes.
Don't worry. Everybody's here, so.
Then we see Pierre-Yves.
You're okay, Pierre-Yves?
I'm just checking the lights.
Mhm.
Yeah, correct. Vous devez voir là, normalement.
Alors, pas encore. Claire is on the phone with Meria and it should be in a few seconds.
We're waiting for. Okay, you just clicked.
Okay.
Yes,
Yes.
we can see you.
Okay, that's good. Okay, I see someone as well. So that's a good start. Okay, so I can we don't need the phone anymore.
All right, thank you.
Okay, very good. All right, that is
Hello.
time, but it doesn't matter. So hello everybody. I can see a few people. Let me. Who is going to start the
Maybe it's you, Meria.
Okay, that sounds good.
Going
So
to start and
maybe. So I thought we would start with a quick introduction for all of us. I can actually perhaps start with myself. So I'm Mary Armori. I'm a professor at the Courant Institute.
Excuse me, but
J'enregistre apparemment.
we have this introduction on air because we are still offline.
You're still
Okay.
online? Okay, so tell me to start then.
I go, hein?
So we say go in like 1, 2, 3, go, and then you can start, Maria. Sounds okay?
Sounds good. So tell me when you want to start then. Now?
Okay. 5, 4, 3, 2, 1.
All right. So thank you all for joining us on this Hangout. My name is Mary Armori, and I thought we would start off each one of us with an introduction. I can start with myself. Quickly, I am a professor at the Courant Institute and also a research scientist at Google. And I have been working on a number of areas in machine learning, but also on speech recognition. Virtually all speech recognition systems in the United States at least are somehow using some of the algorithms that I've been working on. And I think it's with great pleasure here that I'm going to have a discussion with you guys in France, the UK, and I don't know, perhaps elsewhere as well. And so I'm going to start asking each of you to quickly give an introduction. Perhaps Pierre, do you want to start?
Yeah, so hello. Thanks for inviting me to this discussion. So I'm currently head of a team at INRIA Research Institute in France, working on developmental and social robotics. And before that, I had been working at the Sony Computer Science Lab in Paris on topics such as artificial curiosity, social and imitation learning in robots, human-robot interaction, and modeling cognitive development in humans.
Okay, very good. Thank you, Pierre-Yves. Perhaps the next guest speaker that we have, Frédéric Kaplan. Would you like to introduce yourself quickly as well, please?
Yeah, hello. I'm speaking from Lausanne tonight.
Okay.
I've been working with Pierre-Yves for something like 10 years at the Sony Computer Science Lab, and 6 years ago I joined the École Polytechnique Fédérale de Lausanne, the EPFL, where I'm working on new interfaces and new learning techniques, and also a lot of recent development for the iPad and tablets.
Okay, very good. Thank you, Frédéric. So as you can see, we have two sort of guest speakers, Pierre-Yves Boudelier and Frédéric Kaplan, but we also have a number of Google participants. So I would like them also quickly to introduce themselves. Perhaps you can start with David Singleton.
Hi there, my name is David Singleton. I'm an engineering director at Google, working here in London in the UK. I've worked on a number of different things at Google, including voice search and various mobile apps, and today I work on commerce engineering. My interest in this session today is mostly personal, so I recently applied machine learning techniques to build a autonomous self-driving radio-controlled car, and had a lot of folks contact me about that. I'm really interested in a lot of the topics from that perspective.
Okay, very good. Thank you, David. And then we also have Aaron Sean. I don't know in which country you are.
That's right. So I'm actually dialing in from Switzerland, from the Zurich office.
Okay.
And so I'm a software engineer here at Google. I started off working in content ads, and now work in YouTube in the area of discovery. And my doctoral research was sort of at the intersection of machine learning and cognitive science, and specifically I did work in imitation learning and partially involving a humanoid robot.
Okay, thank you. And then we also have Rich Washington, who has already posted also a number of questions and interesting comments. Rich?
Yeah, hi. I'm Rich Washington, as Maria said, and I'm at the Google Paris office. Also working on YouTube, actually on the same project as Aaron is. And a previous project I was working on was biologically inspired algorithms for video understanding. And before I got to Google, I was actually working on AI and robotics, a little bit different. I was working on planning and control for autonomous robots. And in particular, I spent a few years at NASA working on autonomous rovers for Mars.
All right, thank you, Rich. Is there anybody else on the Google side that that is participating? Yes, I can see somebody shaking his hand. Please introduce yourself. I don't know your name, or I was not aware of your
Good evening, everyone. My name is Radu Mihailescu. I'm working at the Dublin Google office. I'm an engineer, an SRE to be more precise. This means that I deal with systems and I make sure they keep working, which did involve a lot of trying to teach the machine how to fix itself before it actually crashes, such that we'll have less to work on it. And I also have a very, very recent involvement with the UAVs, that is unmanned aerial vehicles, with coding a microprocessor to control a plane to fly a path, a mission, and land and take off on its own. So that's basically why I'm here tonight.
Okay, thank you, Radu. All right, so I think we got a quick introduction from everyone here. Now let me get more to the center of the debate. The title of this Hangout is Algorithm and Curiosity. So for those of us computer scientists or mathematicians, algorithm, we know what it means. But what is curiosity? And I'm going to turn to Pierre Boudelier, perhaps, and let him start telling us a little bit, what does curiosity mean, perhaps a little bit more formally in this context of learning and robots.
Yeah, so first of all, curiosity is a word that we use in everyday language, but that is actually not so well scientifically understood so far. And the work we've been doing with Frédéric about curiosity, one of its initial and fundamental goal was actually to progress into the understanding of what curiosity might be or might not be. One particular approach to curiosity is to follow actually what people call in psychology intrinsic motivation, which is basically mechanism in the brain that push us to get interested in some activities for the pure pleasure of practicing those activities, not for the pleasure of getting more money, not for the goal of getting social recognition, not for the goal of getting food, for the mere pleasure of practicing those activities. Like, for example, doing painting on its own and not showing it to anyone, solving crosswords, these kind of activities, and which we particularly observe in very young human infants, when, for example, they begin by babbling with their body, exploring what they can do with their arms, grasping toys, launching them, scratching them, biting them, throwing them, observing how it makes noise, at a point where obviously they have no idea how it could be useful for them for example, getting food or whatever. And so one of the ideas we've been exploring with Frédéric, but actually we were not really the first. This is old ideas in mathematics in the field of optimal experiment design, but who only began to be used to attack the concept of curiosity maybe in the 90s, is the idea that maybe we could model curiosity as the search of information, in the sense that, for example, in a robot, curiosity would be doing activity for the goal of either increasing the quality of the models we are building of the world, the predictive models we are building about the world, or increasing the controllability of the world, which means, for example, having like, imagine a robot playing with a ball, then it would get interesting with playing with the ball by increasing its ability to control how it makes the ball move by making certain kinds of movements. And so we've been developing a whole series of algorithmic models of how we can actually compute what we call, for example, learning progress, or surprise, or competence progress. So maybe Frédéric might want to complete what I just said.
Go ahead, Frédéric.
I think it's... Yeah, you summarized it very well. Maybe another way of saying exactly the same thing is to have a machine, that are always asking themselves, what can I do now so that I learn the most? And all the algorithms we've been playing with, and it's not actually now a family of algorithms, they have the same thing in common. They just try to have a kind of measure, simulated measure about how, among all the action I can try now, have a chance basically to learn the most. And that means that it's very useful for robotics, and this is essentially the first area we've been exploring and showing actually how this principle lead to organized sequence of developmental patterns, but it actually can also be used in many cases where actually making an experiment is costly. For instance, if you have a user, or if you have or if it takes time to do an experiment, you can't just do random trial. You need to have the best possible trial so that you learn the maximum when you do this trial. And so that's another way of saying exactly the same thing.
So I find it's really very interesting. Let me actually place this in the following context. There's a lot going on in machine learning these days, really a lot. And in some way, the area is saturated. Lots of people are doing pretty much the same kind of things. And the sort of things that you guys are talking about, to me, sound very exciting. In fact, I've had discussions with Misha Gromov about connected ideas. And let me be a little bit more, try to reword or retranslate what you said. In a sense, curiosity in that context would be a way of measuring information gain. So suppose that I had a measure of that quantity, the information gain, or the information. Would I come up with an algorithm? Since we talked about curiosity, I'm going to try to connect it to the algorithm. Would that be an algorithm? An algorithm would be, for example, one that would seek to increase, to follow the directions corresponding to the increase of the derivative, the largest derivative of the information. Is that the sort of algorithmic ideas or applications you have been thinking about?
Yeah, that's a very typical example of what we would call artificial curiosity. And actually, as you just mentioned, from a formal point of view, it is closely related to the subfield of active learning in machine learning, where indeed people try to develop measures of information gain, which allow, for example, to collect informational training example to build a model of a given dynamical systems, for example. Another example of measure of interestingness that's also what we call curiosity would not be information gain, but competence gain. So basically, when you talk about information gain, it's mostly related to prediction, predicting, for example, the consequences of your actions. But another kind of thing you can do in machine learning is solve problems, like in reinforcement learning. You define a problem by defining a cost function, an objective function, and then you need to decide, of course, an optimization algorithm to optimize this cost function. But an interesting question is, in most machine learning problems, people assume that there is someone external who provides the cost function. But an organism, a living organism, comes to the world with probably a few cost functions, like getting food, finding social partners, a few of them like this, avoiding pain. But if we observe, for example, exploration in human infants, clearly it seems that they get also interested into things which are not directly or easily related to such innate cost functions. And so it seems that living organisms are able to generate their own objective functions, their own problems to solve. And then, indeed, comes the question, how do they generate those problems and how do they select the interesting ones? And one idea is to say that the measure of interestingness for selecting interesting problems would be to say that the interesting ones are the ones for which the progress in your competence to solve those problems, so in reinforcement learning, the progress into the mean reward you get is maximal. So basically, it means that curiosity can be thought in, for example, a robot which has available a library of cost functions, defining a library of problems, and its life is too short so that it can explore all of them. And then the question he has is which one to select, which one should I explore through curiosity, and the heuristics is basically try to sample them just a little bit, stochastically all of them, and quickly focus on those where the reward increases fastest. So that's some kind of analogy to information gain for predictive models to competence gain in when you want to do control.
That sounds interesting. David Singleton, you heard some of the words that Pierre Boudelier and Frédéric Kaplan mentioned, and this idea of, I would call it algorithmic curiosity, or curiosity in learning. It touches on a bunch of things. It touches on active learning, on reinforcement learning, perhaps in some ways actually information theory, and then Pierre mentioned a number of different experimental designs, all kinds of other areas that have some where people have worked on this kind of things. How do you expect, or how do you envision the use of these sorts of ideas, algorithms, curiosity, within Google? And I'm not asking, obviously, for something really precise, and don't come up with a product right away, but just tell me, where do you think that something like this could be used and actually really work?
Yeah, so I think it's really exciting to think of the ways that we could apply these kind of techniques. One of the things that comes immediately to mind is that we're having a conversation here and we're learning from each other. And I think that if I think about how I do a lot of my undirected learning at the weekends, I spend a lot of time searching for stuff and reading pages on Wikipedia or wherever. And I think that, you know, we want to help users understand their world and, you know, research the answers to their questions and their problems as best they can. And I can imagine that one place that we could apply these kind of techniques would be in allowing the user to interact with a system that is itself trying to explore what is the problem that this user is trying to solve, and how can I best assist in this task. So it's almost like the system is.
Let me interrupt you 2 seconds, David. Could that be, for example, just search? You just basically click on links, browse, you know, just.
So, I mean, I can imagine it in quite a lot of different manifestations. You could easily imagine a search system that is fairly conventional by today's standards, but helps the user kind of tries to understand the ultimate objective that they're trying to satisfy. I could also imagine a system that's able to, you know, continue a dialogue a little bit like this by optimizing for the same kinds of objective functions, right?
Mm-hmm. Oh, that sounds interesting. Rich, what do you, on your side, envision, and why do you think it's an interesting area, that of algorithms and curiosity and this sorts of things? I cannot hear you. Rich?
Sorry. Okay, I'm here. Okay.
Yes.
All right. So as David said, there are things with the user interaction that actually do sound like that might be a useful thing. There are actually, I was thinking of one thing that may be a little bit too mundane, but we have the problem of updating our Street View images.
Yes.
And that's a very hard optimization problem, and having some idea of when it's reasonable to explore for more information might be a more concrete example of something that we might want to see. Basically, one question I have though is on this whole thing is how much of it is based on the user interaction. So, for instance, as David said, we could have this dialogue between the user and the computer. How much can curiosity account for that? Account for the other side of the equation, the user on the other side. And I think Aaron posted a question related to this.
So actually, Aaron, maybe you can mention that question and continue on that trend.
Yes, I don't actually have the set of questions in front of me right now, so I'm not recalling exactly how I phrased it.
So how would you react to what Rich mentioned? And another question I had for you was actually, what connections do these things have with the sort of models for imitation, for example?
Sure. So, I mean, I think, you know, imitation is one strategy for sort of accelerating this kind of reinforcement learning. Obviously, if another agent has already sort of paid the price for acquiring some sort of knowledge about the environment or about things that it could be interacting with, you'd be best to sort of observe what it's already done. Mm-hmm. I think one of the things that makes that tricky, and one of the things in my mind that makes it particularly hard to think about, is the fact that human beings come packaged with so much prior knowledge to begin with. Mm-hmm. And I think it's an interesting open question to ask, to what extent do we sort of come pre-equipped with good models of physics in our heads and good models of controllability for the environment, mm-hmm. versus how much is learned over time?
Sure. So that's definitely an important question. Radu, do you want to react to that? Well, what do you also envision as possible uses of this sort of things at Google?
Well, in my field of activity, we have the age-old problem of having a binary or a service that you have to run, and that binary will need the resources. So striking the perfect balance between giving enough or more than enough or less than enough resources for a single binary, it's always a problem. So a system that could actually take the code and experiment with it on its own and then come back with the results would be really interesting. I'm not arguing for one single binary. We're talking about huge amounts of programs, each in a different language with different requirements. So being able to offload this effort on the computer side would really help the engineering work.
That sounds good. So as you could see, Pierre-Yves and Frédéric, I was sort of trying to ask our Googlers also, because as Googlers, we always think, how do you actually make things work, or how do you take algorithms and run them on large-scale sort of things? So that's one of the reasons why I was asking these questions. But going back to you guys, Frédéric, perhaps, would you actually say in what context you have been using these sorts of algorithmic ideas and perhaps been successful where other traditional learning or traditional reinforcement learning algorithms have not been?
Well, the general context is when you have a space which is much too big to be explored randomly, then there's a lot of beneficial to have like this kind of smart exploration. And another way of explaining what Curiosity is doing is precisely that. I mean, it tries to sample the space and look for what we call with Pierre-Yves progress niches. I mean, zone in that space where progress can happen based on the type of learning techniques that the system is equipped with. So that's very interesting. Each time, I mean, that random exploration is not possible. So to give you a concrete example, and which is linked with the exhibit, we tried actually this on the iPad application of the Fondation Cartier. For this exhibition, we had a situation where we were actually looking into the archives of the Fondation Cartier, several hundreds of documents, each of them with special characteristics, so it's a kind of large space of document. And what we're doing in the application is that we're presenting basically two concentric circles. Let me see whether I can show you that. I'm not sure. I mean, I don't know where you see some.
Yeah, that looks
okay. Yeah, you see the circles?
Sure.
Okay. So basically, you have a kind of content in the middle, and then you have a first circle which we call the relevance circle. So the relevance circle is a kind of recommendation engine, pretty classical. It will just look at the transition users are doing spontaneously. I mean, when they did a sequence of viewing a video of David Lynch and then viewing something about Takashi Kitano's setup, then what would they do next? So that's simply prediction and Markov models, essentially. And we just group in that first circle, what we call the relevance circle, this most likely transition to occur. But a risk is that, as you may know, I mean, there's a kind of self-reinforcing dynamic where it will focus always on the same content, especially also if you add new content in the meantime, which was exactly the case for this application. We started with the first set of content, and then we added additional content, and we may add additional content in the next month. So there's a second circle, which we call the curiosity circle, which is exactly based on that idea that we discussed earlier. I mean, the algorithm tries to see in the space what are the best questions to ask to the user. I mean, it's costly to ask a question. I mean, the user does not have an infinite number of time. So what are the best candidates to submit to the user? And the user may or may not choose them, but in any case, we will increase the learning and decide not to show them anymore, or maybe to show them in the relevance circle after that. So it's a first attempt. It's on a database which is big but not huge. But that was an interesting use of that principle in a kind of search, not search by word, but search in a guided. I don't know whether you have a word at Google to name that type of search, like navigation between content.
It sounds good. So that was an interesting example. Pierre-Yves, do you want to add other, anything else to that? Examples or cases of success that could be actually, obviously this is an area that's just starting, if I understand, or you guys have been working on this sort of things maybe for several years, but it's still in its infancy, if you agree with me. Are there other cases, successful examples that you could mention?
Yeah, so actually to rebound on several people mentioned social and imitation learning. There are, and human-machine interaction. There are actually various important links between curiosity, social learning, and human-machine interaction. First of all, as we've been experimenting with Frédéric, we've been showing that an autonomous machine, such as a robot, exploring its world through curiosity might not only get interested into physical interaction with objects, but might discover that certain particular objects around, people, humans, react in particular manners when, for example, you vocalize or you produce a text to them, such as in the application just shown by Frédéric. And then, in a way, by creating such an interaction, not only the machine becomes interested into social interaction, but structure can emerge from both sides. This is something that's being experimented right now in the application of Frédéric between basically a computer that is exploring the reaction of readers through curiosity. And then this is also, for example, what is happening in the ergo robot experiments that was shown at the Fondation Cartier at the exhibition on mathematics, ergo robots being a term inspired from the ergo systems of Gromov, where actually you had little robots who were sometimes playing with physical objects through curiosity, then sometimes interacting among themselves, inventing languages, but also sometimes trying to vocalize towards the human visitors coming in front of them, and then trying to predict their reaction. That could be gestures or speech or whatever. And through this interaction, which actually with Frédéric we explored with robots a number of years ago, some structured interaction can be formed, the elements of elementary communication, which is not only interesting from a fundamental scientific point of view, but which actually makes that the structure of this interaction, because in it there is also a human, which also have a brain which is sensible to curiosity and activities where there is progress to be made. It makes that the interaction by itself becomes intrinsically motivating and interesting for the human, which means that basically those ideas of curiosity, they are not only useful for efficient information gain, like for example having a machine only ask the relevant question at the relevant time to a human for increasing its knowledge, but this concept of curiosity is also fundamental for creating a pleasant and fun interaction between a machine and a human. For it to be fun on the long time, it must be intrinsically motivating, and then we need to understand fundamentally what it is if we want to create such interactions.
Okay, so that sounds interesting. There are several things that you mentioned. That I'm gonna pick a few words that you mentioned. One is structure, and that actually relates directly to a discussion I've had with Misha Gromov about this sorts of ideas. And then another one is fun. I mean, we already had trouble sort of trying to define curiosity, but now you're adding one other word that we're actually interested in, of course. But how are you going to define fun, particularly for a computer? But don't answer that. I was going to ask just all of you at the same time, just tell you this idea of structure, which in the way that you described it is more like a structure that the dialogue, the interactions of the robots, perhaps with people, would uncover that structure. That structure would come out of these interactions or something like that. But let me give you another specific example. Suppose that you're a mathematician, or rather you're a child who's interested in mathematics, and you draw geometric pictures on the board. There's structure, obviously. I mean, I draw a triangle, a rectangle. There might be different corners. And so in the same way, a robot, this is a different type of structure that I'm talking about, obviously, but I just wanted to pick on that word. Do you think that there are ideas there for implementing or coming up with an algorithm that would try to actually look for, if a mathematician or even a child mathematician looks at a triangle, he's not going to look at every point of the triangle. That's not going to be the interesting thing or the curiosity. The curiosity perhaps is going to be for the corners, the particular shape of the triangle. There are different types of triangle. So what do you think of that? in other words, let's say that you want to have a robot that understands the notion of triangle, understands the notion of a rectangle, practically a robot that starts understanding mathematics. And there is geometry, there's structure there, real structure, and something that we can define.
Yes, maybe one short answer, and then maybe Frederick wants to add something. Actually, it seems that there is a very strong relationships between what happens in the brain of scientists and mathematicians in particular when they do their science, and what happens in the brain of young infants when they play with their body and with objects and humans around through curiosity. It seems that in both cases, they are searching for structure and for improvements into their understanding of the outside world. And in both cases, it seems that it is the improvements about the or the discovery of regularities in the world that is producing internal rewards in the brain. And in the case of mathematics, it is an experience that is often described by the mathematicians. They are studying complex mathematical objects. They don't see relation between them for a long time. And at some point, an idea allows to relate all of them around the same compact invariant property. Then there is some kind of aha and a big internal pleasure. That's the consequence of this compression of an external structure. And competence progress, which is actually also a term used by a colleague of us called Jürgen Schmid-Huber, who is also studying those ideas of curiosity. It seems to us that the models we are using could potentially be applied to explain scientific exploration by itself. I don't know what Frederick thinks about this.
Yeah, I wanted. Yeah, I wanted to add this idea that actually, yeah, Jürgen Schmid-Huber is putting very clearly. I mean, this idea that actually understanding is linked with compression. Compression is the way you can actually represent with very little error an apparently complex model with very simple rules. And if you want to generalize the predicting model, you could see them as search for compression solution. And this, I mean, the example of the triangle you gave, but also very generally, I mean, the possibility of building a model of anything in the environment is linked with the possibility of actually building a small program that would be able to reproduce the shape, the structure you've been seeing, but with much less bits, I mean, if you want. So we can, that's yet another way of looking at the same thing, and actually there's a lot of theory about aesthetics that can be built about the relationship there is between an apparent structure and its and the possibility to compress it into very little information.
Certainly the idea of compression or having a compressed representation of a concept, that's been around in machine learning for a while. And in fact, it's the foundation for a number of learning algorithms and theory. Let me turn to some of our Googlers and ask them also, do you believe in this sort of things? You guys who are not Pierre Boulier and Frédéric Capon, do you think that these kind of algorithms can actually work? I mean, let me give you some negative things potentially, right? I mean, leave a robot be curious. It might actually go out and think that it's very interesting to go and look at a particular corner of a room. Is it clear that it's actually going to be more curious about, I don't know, the TV that is in the room, or more interested in the person in the room that he can interact? How do we know that the curiosity is going to be directed to something actually that we view as being interesting? What kind of things do you think, again, in the context of, I don't know, playing with a Google phone or this sort of things, how do you think that this kind of algorithms could actually work?
So I think that it is plausible. I mean, I find the example that you gave with the triangle kind of baffling to begin with. Just to even think about a triangle in the abstract, and obviously a computer seeing it as a series of pixels, and you were really focusing on the structure there, which is very simple. But I mean,
sorry to interrupt, but just to be very clear about that example, what I wanted to say there was that somebody interested in geometry will not be interested in there are infinitely many points in that triangle, just like you said, the space of actions could be infinite in many learning cases, but certainly that's not what a person would be looking at. So go ahead.
So many machine learning algorithms are able to just take this baffling amount of data and through seeing how each of these features plays out in actually coming up with a conclusion in any case, really, automatically focus in on what's important. So I think that the ideas are certainly compelling. I'd love to hear a little bit more about how you put some of those ideas into practice to, for instance, make the exhibit that you had that was doing that interaction with humans and conversation development work.
Yeah, Frederick mentioned some of that. We should probably ask you a little bit more about this. But turning back to some of the our other Googlers here, Rich, Aaron, and Radu, I'm going to come from learning theory and tell you that part of what Pierre Goudeillet and Frédéric Kaplan are describing, just part of it, is relating to active learning. And there's almost any kind of negative news that you want in learning theory about active learning. There's basically nothing that is positive. Everything, in practice, it might sometimes work, but in theory, it's almost always negative. There's nothing that is really positive.
But I think one of the sorry to interrupt. One of the I think underappreciated things about all this is that if you're an active learner on your own and you're trying to decide on sort of what the interesting parts of the environment are to explore, you may well be lost in a very complex environment. But if you have other agents who are willing to cooperate with you and actually show you what interesting samples of the environment are, then potentially, that's a very fruitful approach. So I guess the real question is, how can you design an agent such that humans actually want to show it interesting samples and show it interesting sort of parts of the environment to explore?
So are you thinking here of the ideas of imitation or apprenticeship?
Exactly.
Yeah.
Yeah. If I may just rebound, actually you are right. There are many reasons theoretical reasons that if you do only active learning in a big space, then you will have a lot of troubles. So actually living organisms, they don't explore their spaces only through intrinsic motivation and curiosity. Curiosity is highly constrained by internal biological mechanisms, which are on the one hand the innate cost functions that I was mentioning, like searching for food, this kind of thing, but also things like maturation, like for example a human baby who is discovering his body does not have access at the beginning to all his muscles, but progressively there is myelination who makes that only, for example, muscles in the neck are available, and then in the shoulder, and then in the knee, and then in the hand, and this progressively grows the sensory motor space in which curiosity can explore. And external to the body, you have of course social partners. For human infants, parents, and for robots, just any humans, who are there to guide and to bootstrap curiosity-driven exploration and to put the walls inside which it's going to work. And so basically what we are working technically in the recent years about curiosity is not so much about curiosity by itself, but how it can be embedded in a complete cognitive and learning architectures and in a social environment in which it actually can work in big, large spaces.
Mm-hmm. No, we cannot hear you anymore. I don't know if it's Pierre-Yves. Can you hear us?
I just stopped, yeah.
Okay. So we still cannot hear you, Pierre-Yves. I don't know.
Okay.
Everybody else, can you hear me? If you can hear me, raise your hand. Okay. So some people can hear me. That's good. Okay. Pierre-Yves can hear me too. That's good. So we're getting close to the end of our conversation, and I didn't mean to leave us all with negative news, obviously, or negative words on that. I think it's a very exciting field and area, although I still think it's probably just the beginning, and that makes it even more exciting. But what I meant to say was that there's still precisely a lot to do here. I mean, one of the goals of that Fondation Cartier's exhibition was the mathematics and enjoying mathematics in general. And if you think about this, it seems there's a lot of problems here to solve mathematically. for talking about curiosity, for talking about learning, where the objective or the reward itself, in a sense, it's learning. Am I correct to say this, Frédéric? Or
yeah, it's maximizing learning. Yeah,
it's maximizing learning. So the reward itself. So in a sense, it's compared to all kinds of traditional supervised learning ideas and algorithms. Here, there is no objective in a sense, or it's learning without an objective, unless the objective is just learning itself. By the way, this connects very much to something that in the old time, even in the language in Latin, the word for learning actually means learning to learn. So it actually connects very much to this sort of ideas. So before we finish up our conversation, I wanted to ask you each, if you had to start, I mean, in the case of Pierre-Yves and Frédéric, I think that's clear. These guys have been working on this sort of ideas, and they have already implemented things. But if you had to tomorrow go and put together something based on these ideas of algorithms and curiosity, what would you do? David, what would you start doing? I'm just worried that tomorrow, just by tomorrow, you would actually come up with something and show us something.
I think I would try to develop the project I'm kind of halfway through with the car, which drives itself, to try to find maybe the places that it's most successful at making progress, and how to find the parts of space where it can make most progress.
Okay, that sounds good. How about you, Aaron?
You know, I think there's a lot of different topics and a lot of different areas where I could foresee that being useful. You know, I think in particular something where you could actually have a system that would help guide you as you're searching for you know, questions to ask or pieces of information that are interesting to you. Something that would be sort of an interactive you know, sort of project that would suggest questions to you that you might find interesting would be a cool application.
Rich, would you think that this could be interesting to implement ideas based on that in the context, I don't know, of games, for example?
Games might be interesting. I was actually thinking, since I'm working on YouTube, of how to suggest interesting videos to users, which is, I guess, kind of a game. But we have a big space, and it's not clear how to explore it. And it might be interesting to use these ideas to choose different videos that might be of interest.
That sounds interesting. Radu, how about you?
Well, a very good breakthrough would be if the system could actually advise which services can be run together. We humans seem to be very good at calibrating one machine for one service. However, when you have thousands of services and millions of machines, the interactions that occur make it very, very difficult to be able to predict that you will be able to offer the same level of performance the whole year. So it will be very interesting if the machine could actually use the knowledge accumulated in using private experimentation and tell you that, hey, it's not a good idea to run those 3 services on that particular architecture because they will start stepping on each other's toes in like 6 months' time. That would be a breakthrough, and it will help the engineering world.
That sounds interesting. Pierre-Yves and Frédéric, as you can see, you have lots of customers already, lots of people who are interested in continuing on your ideas. It's time for us to wrap up this conversation. I think it's very exciting. You could probably invite us to look at some of your publications, and we can probably just go to your website to look at this, both of you guys. And I'm sure that in a few years we're going to have another Hangout, and this time it's going to be about all the amazing things that have already come out of this work. As for me, I'm particularly interested in the mathematical aspects of this. And I want to thank you both, particularly our guests, Pierre-Yves and Frédéric, and everybody else, Googlers, for having been on this Hangout. And I hope we're going to have other occasions, other opportunities like this. Bye-bye. Take care. So I don't know if you can still hear me.
Yeah.
Yeah. So we stop officially. We